What do we expect to see? This is the calculation that provides the theory for decay. If we decide to obtain element 116 or element 118, this is what the calculation looks like. Here is the number of neutrons, and here is the number of protons. For example, like it was in Darmstadt when they obtained element 110. Let's say lead-207 is irradiated with nickel. Then element 110 is obtained. It goes through alpha decay, becoming element 108, goes through another alpha decay, becoming element 106, which then undergoes spontaneous fission. Here is the chain. The yellow zone on the contour map is the zone of alpha decay, while the green zone indicates spontaneous fission. The lines indicate the half-lives in seconds. We will irradiate curium with calcium-48. We are here. In the yellow field, alpha decay takes place twice, after which the third alpha decay touches the green zone for spontaneous fission. If we're talking about element 106, then we should see this picture. But if we're talking about element 108, we irradiate californium-49 with calcium-48, and the same pattern is repeated, 1, 2, 3, until we reach the green zone. Let's see what happens when working with even and odd-numbered isotopes. When we irradiate curium-248 with calcium-48, there will be 1, 2, 3 alpha decays and 4 spontaneous fission. When we irradiate curium-245, then we move a little to the left, 1, 2, 3, 4 alpha decays with spontaneous fission at the border of the green zone. Either spontaneous fission or maybe alpha decay can take place. If there is alpha decay, then the chain will continue further, one more taking place at the border, another again taking place at the border. This is the chain. 1, 2, 3, 4, 5, 6. 6 generations. Mother, daughter, granddaughter, great-granddaughter. This is an excellent characteristic for identifying this nucleus. We can always test what we see. If these are alpha particles, then remember what I talked about in the first lecture when I mentioned Gamov's theory, the theory of alpha decay. And recall the Geiger-Nuttall relationship, where the alpha decay period, or decay probability, is very dependent on the decay energy. Indeed, these were light isotopes obtained in Darmstadt. Look how well they fit into the prediction of this theory. No worse than those obtained with calcium-48, when we are talking about elements 108, 112, 114, and 116. Therefore, we can always test whether it was an alpha particle or a false signal. The same goes for fission fragments. We know that there is fission when uranium turns into fermium, that light fragments increase all the time and heavy fragments change slowly. This is called asymmetric fission. At the point where they are predicted to meet on the graph, there will be symmetrical division, and then they can diverge again. Here is a graph depicting the mean total kinetic energy of the fission fragments in neutron-induced and spontaneous fission. This is the asymmetrical part, and it can continue to this part. And if there is symmetrical division, then it will be in this area. That is, we expect quite large fragment energies here. In general, the graph becomes very clear. This means that alpha decay is about 8, 9, maybe 10 megaelectron-volt. Here you can see 8, that is 10 megaelectron-volt, 9 megaelectron-volt, 9 megaelectron-volt, and 8 megaelectron-volt. And then suddenly it increases to 230 megaelectron-volt. It is very difficult to confuse this graph with anything else. It is very unusual because in no other region of nuclei, the lighter region of nuclei, will you ever find a case where alpha decay occurs first, and only then does spontaneous fission begin.